Good morning, everyone. Hopefully you had a good afternoon yesterday. It was a nice sunny day. If you want to throw in a green check in chat, if you had any questions from the learning guide from last day, you want to throw those into chat as well. We'll get going here. Kind of looks like maybe a few people are maybe sitting in the Blackboard for homeroom, kind of waiting for Mrs. Wood to get going, but I'm sure they'll trickle in here eventually, so I'll just go slow to get things started. It doesn't look like anyone has any questions about the learning guide, which is always a good thing. Even if it's just something that's kind of, you're just wondering a little bit about or something like that, you could put it in and maybe I could clarify things a bit. We do have lots of time today, so we'll see how much we can get through. Taylor's going to look for a question. See that everyone's giving me a green check mark, which is good. And a few people are starting to move over, I have a feeling, from the other room. So just to kind of recap where we were with the learning guide. We have, or should have, done the number system stuff at the top. And then we have the number line stuff, which is just finding a place for these numbers on that number line. Okay, Taylor and Abby both have questions, so we can go through those in a second. Evaluating radicals, stuff that we did yesterday. This is kind of like estimating either side of the radical and then figuring out which perfect squares it's between, and then evaluating and then doing some basic calculation stuff. So that's kind of where we've got to this thus far. A few questions coming in here. So Taylor, for the number systems number 2, I don't get the fractions. Okay, I'll do that for sure. All of the fill in the blanks. Do you want to give me like a specific number, Abby? And then maybe I can help you out there. So number systems, number 2, let's go look at that. Abby's going to throw in a specific number for me. Number systems, number 2, identify the categories for each number shown below. How do we do equation square root? Question 1A of lesson 2. Okay, these are some good questions. 2I, perfect. I think we have some questions about this number 2, and Abby's asking about number 1. Which section, Abby? The very first one, the number systems number 1, or a different section number 1? All right, so going back to the image here, it's the same one that we had in lesson number 2, I believe. Nope, lesson number 1. Same sort of circles. So these are different types of numbers. So we have our natural numbers in the middle, and then we have whole numbers, integers, rational, and irrational is anything that doesn't fit into one of those categories. So if we go back to the learning guide, and we see that we have a number like 0, and we need to identify where 0 fits into the number system. So as I was kind of explaining it when we were going through it in lesson number 1, a number like 0 wasn't one of our natural numbers. So we can't include it as a natural number because it's just not a natural number. When we're just counting things, 1, 2, 3, we never go 0, 1, 2, 3. That's just not how it works. So this is a whole number. That is the smallest category. Then if we get to the next step, it's also an integer, because that's the next bigger category. And it's also a rational number. So if I just jump back over to this image, if I think about 0, 0 fits in right here. There's my 0. And it includes the whole numbers, integers, and rationals. So it's including all of the bigger circles because these big circles all include that 0. It's not a natural number because by definition a natural number has to exclude 0. Maybe we'll do another one. So 2K and 2L either. Okay, perfect. So we got a bunch of questions here. Excellent. Number 2, maybe, I don't know, let's pick a different one. Something like maybe F. 387, 387, 387. See that the 387 repeats itself, and oh yeah, that's a good point. So Abby saying the same thing. Can decimals be integers as well? By definition, a decimal isn't an integer because integers are just like 1, 2, 3, or -1, -7,023. Those are integers. As soon as we go into a decimal, it's just a rational number. And Alex brings up a good point. Isn't it also a real number? Which is an interesting sort of idea to kind of talk about. So if we look at the image number 1 here, everything is a real number. So what defines a real number, or maybe we should look at maybe what defines an not a real number or imaginary number. So essentially all of these are all going to be real numbers. I don't see any that aren't real numbers. So they are all real numbers. I could write it down for all of them, or I could just put it like that. These are all real numbers. The one thing I want to mention about F is that the decimal is repeating itself, 387, 387, 387. And you can, what's a fake number, Alex? This is kind of something you won't learn. I don't even think we talk about it in Math 10. I don't even remember where I first learned about it, maybe like Physics 11 or 12. There's something called I, and it is it's called imaginary number, which is kind of the opposite of real numbers. And we've talked a lot about how we can't take the square root of a negative. So mathematicians are kind of crazy people, and they thought, what if we could take the square root of a negative number? So they invented a whole nother system of numbers. So not the real number system, but the imaginary number system. And it's based around this idea of taking the square root of a negative number. And they call it I, and I is just the square root of -1. That is what I is defined as. And you guys definitely don't need to know this. So they graph these things, they deal with problems with these imaginary numbers. So anytime you have a negative under your square root sign, it's an imaginary number. So kind of like a really crazy idea that you won't really get into in high school. Not a lot. We use it in electricity. So a lot of dealing with kind of electrical currents and things like that, how they flip back and forth uses imaginary numbers. Can't really think of a lot of other applications off the top of my head because there aren't a ton in our everyday lives that we're kind of running into. So, but back to F. Hopefully that answers your question, Alex. I'm just going to erase it so nobody gets confused later. This point 387, 387, 387, it just continues and continues. So it turns out that this is a rational number, even though it continues on forever. So that's a bit of a tricky one. Because it's repeating, we could write it in the form of a fraction. And I'm not going to get into it because it's something that kind of takes a lot of time and it's a bunch of steps and you don't really need to know how to do it. As long as you could recognize the fact that there's something repeating in that decimal, that means that it's going to be a rational number, as long as it repeats. If we look at the next one, letter G, 0.377388499. This doesn't look like it is anything that's kind of repeating over and over again. So it's likely going to be an irrational number. You could put down real number for all of these as well, if you wanted to. There's nothing wrong with that. But again, it's just, they're all assumed to be real numbers because it's all part of the real number system. So Taylor asked for 2m, 5/8. So is this a real number? Rational number, irrational. 5/8 is a fraction, so we know it's definitely not an integer. So if we look at our set of circles from the first lesson here, it's not a natural number because it's not one of my counting numbers. 5/8, it's a fraction. It's not a whole number because it's a fraction of a number. It's not an integer because those are all of my negative and positives. And it only falls into this rational numbers. It's a fraction. It ends, and that's just kind of what it is. So we would call it a rational and a real if you wanted. But it's nothing other than those two things. So it doesn't fall into any of the smaller circles. You got the big circle, but it's not in any of the inside ones. Hopefully that helps that. Let's see if we have some other questions here I can get to. Isn't also a real number. We kind of dealt with that. Is there any numbers that only go in the real category and no others? No. If you are, you could be a rational or an irrational, and yeah, you're definitely a real number. So I'm thinking that's a really good question. There are, not that I can think of, there are no numbers that can go into a real category and no others. Yeah, that's a tricky one. A fake number, we did that. Could you put in that as a real number? Anyways, yes, Abby, I think I answered that. Can decimals be integers as well? No, and 2k and 2l. And then Taylor wants the fractions. So 2k and 2l. All right, so k, if we take the square root of 3 in our calculator, what does that look like? Well, I'm going to just fire it in here and just get an exact or an approximation. Square root of 3 is going to be 1.732 blah, 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 blah. It just keeps on going on forever. So it's a decimal. It's not a perfect square, so it's not going to be a whole number or an integer. And because the square root of 3 continues on forever, it falls under our irrational category. It's by definition an irrational because it doesn't terminate and it just continues on forever. So that's what an irrational number is. We can't rate it as a fraction. Number L is -1. Remember, we can write this as -1 times the square root of 81. We know the square root of 81 is 9, and then -1 times 9. So the answer to this, if we were to simplify, it would be -9. And that's an integer because it's a negative number. That's the smallest category it fits in. It's also rational, and it's real, if you wanted to think of it as a real number, you could. So just kind of a little step there to move things on a little bit further to get to kind of where you want. There was some, Abby, number 1, evaluating irrationals, DIMN, 2 and 3 in the section, also fill in the blanks. And then fractions. So hopefully that helps. Number 3, list any of the numbers in the previous question that terminate and repeat. So when we talk about things that terminate, these are ones that end. Repeat are things that don't end, so they go on forever. Is anybody else running into the problem that Avery just posted up there? Looks like evaluating radicals. Okay. I think my learning guide is different. I don't have numbers on those questions, just of blank squares. Is it possible that the wrong learning guide? I don't think there's any other ones open. Maybe you just downloaded one of the practice sheets instead of the learning guide? I'm not sure. All right, I'm just gonna keep going on. If you wanna clarify things, you can just keep typing into chat. I'll hopefully get it. So there was a question 1, 2, and 3 in the evaluating radicals section. So I'm going to go down. We'll look at a couple of those. Estimating radicals. Did somebody ask about estimating radicals? Okay, so it looks like there might be an issue with how it's downloading on your computer. Maybe like a PDF issue. What did you want from estimating radicals there, Taylor? And then I can get into the evaluating radicals. Estimating radicals, number 1. What is the difference between squaring a number and taking the square root of a number? So squaring a number, if I had, say, like 3, if I squared it, I'd go 3 squared. And that just means 3 times 3, which is equal to 9. If I were to take the square root of a number, I'm asking what number multiplied by itself gives me 9. So in this case, 3, because 3 times 3 gives me 9. So the squaring and the square root are opposites of one another. If you square something and take the square root, you should end up at the same spot. So in this case, 3 squared is 9, square root of 9 is 3. Number 5, what is the difference between cubing a number and taking the cube root of a number? Same sort of idea. Let's pick a number, nice small one, easy to deal with. 2 cubed is 2 times 2 times 2, which gives me 8. And if I were to take the cube root of 8, I would ask myself, what number multiplied by itself 3 times gives me 8? And in this case, it's just 2. So the cube and the cube root are opposites of one another. If I take something and cube it, and I take the cube root, I should end up at the same number, in this case, 2. Blank squares fraction. So, estimating radicals known 1 and 5. Number system 7. Let's have a look at number system 7. Are all rational numbers integers? So rational numbers and integers. Let's go back to our image here. So rational numbers is this big circle, and then integers is contained within it. So can anyone think of an example of a rational number that is not an integer? So thinking about any number that we could count as a rational number, but it wouldn't be an integer. So we'll go, no, not all rational numbers are integers. And Abby, off the top of her head, thought up one, which is 0.4. So any decimal number that terminates or repeats would be considered a rational number that's not an integer, because integers are whole values. So like negative 27 or positive 12 or 1 or 0, those are all of our integers. And anytime we go between an integer, so between like 0 and 1, you get 0.4, that would be a rational number still, because we could write it as a fraction. But it's, oh, I put this in the wrong spot. Are all rational? No, we can have decimals, which terminate. So 0.4 or 0.4444. That repeats. Decimals which terminate or repeat. So those would both be examples of rational numbers that are not integers. Okay, estimating radicals number 1. I think I did that. Yes. Evaluating irrationals. Somebody have a question about the evaluating irrationals? My chat is all giant sized here and I can't see as much. Evaluating radicals 1, 2, and 3. I think we're all right. You did number 2. Okay, so I'm going to just pause there for a second. I've kind of lost track of the questions. I think I've got through most of them. If anybody has anything from any of the other sections or something you still don't get, you want to throw it in the chat, I'd be happy to do it. If not, I will move on. The third question regarding the square root of 98. Up here at the top, third question. That's not it. That's not it. That's not it. Evaluating irrationals number 3. Okay, that's helpful. A cube root of a negative is always that guy? Oh, it's on the worksheet. Evaluating irrationals. Now you guys are getting me all mixed up. So cube root of a negative, maybe Shayna, you can write in the question. I don't have that sheet loaded into my my notepad here, so it might be difficult for me to work through it. I've understood so far that it's the square root of 98, but I don't know what beyond that you want me to do with it. Says negative square root of 98 like that, and then it's asking you to like calculate it, simplify it, identify, or is the, what's it asking for you to do? Give you a second, maybe you can help me out. Evaluate perhaps? Or is it like an estimate the value of? Determine the 2 closest whole numbers and estimate. Perfect. So if I wanted to break this down, I would go -1 times the square root of 98. Because anytime I have a negative, I just have that -1 out front. So I'm just going to kind of ignore the -1 for now and just deal with the 98. So what 2 radicals, or sorry, what 2 perfect squares, I should say, are on the other side of 98? So if I think about 98, what's lower than it? If I had 9 squared, I'd have 81. And what's higher than it? I have 100. So it's between 9 and 10. I would say 98 is probably closer to the 10 end of my spectrum. So if I had to pick a number on the number line between 9 and 10, I'd say it's probably really close to the 10. So maybe like a 9.9. So now I've estimated it. I'm going to put it back into this. So I have this -1. And then I've estimated this as 9.9. I'm just going to do the multiplication and get -9.9. And of course, it's just an estimate. So if you had like -9.8 or something like that, that would be completely fine. Does that help you, Shayna? Abby, sorry, based on the irrational numbers. I'm getting the sections mixed up. Okay, perfect, thank you. Okay, I'm going to go on to the lesson. Unless I'm misunderstanding what you were asking, Abby, I think I've evaluating irrational numbers 4. Determine the integer that each of the following would be equal to. Show your work. For sure. We can do maybe 1 or 2 of these. Just get this out of the way. So kind of like what we did in the practice. And just so I'm making sure I'm understanding, Abby, you're good, or do you want me to do another question? I just don't want to forget about you. So while I'm doing maybe a few from number 4, if you want to write in like you're good or section and number. Maybe let's do, I think I actually did C right in the lesson, so let's not do that one. Maybe I'll do like, I don't know, let's do this one. We'll do B and then maybe H because it's similar. And then we'll do one of these multiplication ones down at the bottom, like E. So B asks the square root of 169 minus 25. So if I break out my calculator, I go 169 minus 25, and I end up with the square root of 144. So just treating my radical sign kind of like a bracket, doing whatever's inside of the bracket. I know the square root of 144 is 12. So that's going to equal 12. The square root of 169 is going to be 13. I'll do this over here. So I get 13 minus 5, which is 8. So again, we found this last day that these two things aren't equivalent when we're adding and subtracting. So 12 is not the same thing as 8. But when we multiply and divide, let's see what happens. Down here, 25 times 144 is going to give us 3,600. So I'm going to have the square root of 3,600. And I know that that's going to be something to do with 6. So if I take the square root of that, I get 60 because I recognize 36 as being a perfect square. If I do these separately, I get square root of 5. 5, square root of 25, and then 144 is going to give us 12, and 5 times 12 gives us 60. So these things are the same when we multiply and divide. So hopefully that helps you out a little bit, Taylor. Abby got booted out, now she's back, and she's typing, Mr. Borden, I'm understanding, or please do this question because I don't get it. Give you a second, Abby. I'm good. Thank you. That is good. So I'm just going to go through the lesson number 3. If you have any questions about the work that I didn't go through, maybe just wait till the end. We might have some time because we have till 10:20 today. And I always say it's not going to take that long, and it always ends up taking that long. But I'm optimistic today. This is stuff that's pretty straightforward. An interesting thing about this lesson 3 is that a lot of the things that we do in lesson 3 will kind of build the foundation for the rest of math. It's not difficult stuff, but it takes some practice being able to recognize the radicals and the perfect squares and things. So this is kind of the one section where knowing your perfect squares is really going to help you out. So fractions can be written many different ways. For instance, 4/16 can be written as. Some other ways to write this. You can think about it as simplifying it. So if I have 4 and 16, 4 goes into both of those. I could write that as 1/4 if I divided both the top and bottom by 4. Some other ways I could represent that. Taylor got the 1/4. Does it have to necessarily get simplified? No, I can make it larger. I could multiply both the top and bottom by something, and it'll still give me the same decimal, 0.25. So I could write it as, if I multiply both the top and bottom by 2, I could get 2/8. 2 divided by 8, still 0.25. I could write it as 3/12. I could write it as 5/20. I could write it as 40/160, or I could write it as 1,000/4,000. It doesn't matter. 0.5 is going to be, that would be like 1/2. So we're not quite the same thing on that one. 1/4 is 0.25. 1/2 is a half. So there's really no limit to what I can multiply both the top and the bottom by. I can make it bigger, smaller, whatever, but it's always going to be the same thing. If I plug the value into my calculator, I'm always going to get 1/4 or 0.25. So you can do the same thing with radicals. We saw this last day. We did a couple of examples of this. So if I go 9 times 25, I plug that into my calculator. I end up with the square root of 225. If I take the square root of 225, I get 15. If I do the same thing separately, square root of 9 is 3, and I'm going to multiply that by 5, I end up with 15. So the idea here is that if we have a radical, we can, and there's multiplication under the radical sign, we can break it into two radicals, or we can leave it as one. And sometimes it's going to be really handy to be able to break it down into two smaller radicals, because multiplication doesn't matter what order you do it in, so you can either do it under the radical sign or you can simplify and then do the multiplication. So it kind of gives us a little bit of flexibility in answering some of these questions. The same thing exists for our cube roots. If I were to take the cube root of 8 times 27, I multiply these two together and I get 216. Need to figure a number multiplied by itself 3 times, which equals 216. And this is kind of what I was mentioning at the top. If you know your perfect cubes really well, you should have a little light bulb go off in your head and you think, oh, 216, I've seen that before. Or if you want to have your lesson from last day with the table at the top of it, kind of hanging around there, you could figure, just look in the chart and look at it and see what it was. So the cube root of 216 is just going to give us 6. You could plug it into your calculator, cube root 216. What does it equal? 6. Don't be afraid to use your calculators in this section. Or I can think of it this way. What number multiplied by itself 3 times gives me 8? So if I go 2 times 2 is 4 times 2 is 8. That's going to be 2. And then I'm multiplying the same number by itself 3 times to give me 27. I get 3. 2 times 3 is 6. So I end up with the same answer for both of these examples. If I'm multiplying under my radical, I can break them up or I can keep them together. So you're probably thinking, why are we doing this? What are we ever going to use this for? And I'll get to that here in a second. So this multiplication property of radicals is going to be just kind of a fancy sort of definition of the property that we just looked at. So you can see it kind of gets really confusing. N is just a number. It says a natural number. We know what natural numbers are now. Anything excluding 0, so 1, 2, 3, 4, 5, 6, 7, 8. So natural number. So we could have the cube root, or we could have the 4th root, or the 27th root. It doesn't matter. As long as it's a natural number, we can do it. And A and B are just two other numbers, and A and B are just being multiplied by each other. Some calculators will do it. That's a good point, Damon. Some calculators are smarter than others. Devin. You can just put the square root of 9 times 25 in and it works. Some calculators kind of don't like these things and the order of operations get kind of mixed up and you get the wrong answers. But for these ones, because they're multiplication, generally it should work. But it's not going to help us that much because we're going to have to kind of look at these questions a little differently. So we can use this property to simplify square roots and cube roots that are not perfect squares. That's the kind of the key here. We're dealing with non-perfect squares or non-perfect cubes, but have factors that are perfect squares and perfect cubes. So we're going to use the idea that we can multiply these numbers under a radical sign to break them apart. And if we can find a perfect square, a perfect cube under there, we can just make them a lot simpler. So let's look at a few examples of this. We need to kind of define these things as mixed radicals and entire radicals, kind of like mixed fractions and entire fractions. You guys spent a lot of time doing that in grade 9 where you'd go back and forth. So a mixed radical is going to be a number written as a product of a number and a radical. If you wanted to think of an example of this, I would write it as maybe like 2, that's my number, times the square root of 3. An entire radical is going to be kind of like, if you think about the fractions idea, you have a mixed fraction, you have a number and then a fraction. And then if you had an entire fraction, everything's over the fraction. So it's just going to be a radical with a number under it. So we could write square root of 12. That would be a good example of that. Okay, so finally getting to some examples here. It asks us to simplify each of the radicals. I'll do a few. I'm sure you'll kind of pick up on it really quickly, but you look at it and you say, square root of 63. I don't see any perfect squares there. 63 is not a perfect square. So how could I possibly simplify this? I'm going to write a little note here for us, a couple stars next to it. So we're going to look for perfect squares. So thinking about our multiplication tables back from whatever, grade 6, 7, I don't even know when you learn multiplication tables. You need to be good at your multiplication tables and you need to know your perfect squares. So what number, which is a perfect square, goes into 63? So the little numbers going through my brain and I think to myself, 9's a perfect square and that's a factor of 63. So I know I can break this down a little bit. From the law I just wrote down, I know I can break it into 2 separate radicals. So Ava's got 9 multiplied by 7. So instead of writing it as 63, I'm kind of going to work backwards and say, 9 times 7 is 63. And then I'm going to take it another step here, and I can think, I can actually write this as 2 different radicals. So square root of 9 times the square root of 7. And then I can take the square root of 9 to get 3 times the square root of 7. Now the 7 has no perfect factors, perfect squares that factor into it. So I'm not going to be able to simplify this any further. I'm just going to leave it as 3 root 7. That's as simple as it gets. I've taken the largest perfect square out of 63 that I could, and 9 was it. Let's look at another example. We can do these in lots of steps, or we can just do them kind of in one step. So the square root of 200. What are the perfect squares that go into 200? How can I break this down into 2 numbers that multiply to give me, how did I get the 3? I just took the square root of 9 to give me 3, because I know 3 times 3 gives me 9. Ava's on it. 10 times 20. Taylor, you're right, 10 times 20 is 200, but neither 10 nor 20 are perfect squares. So I'm thinking numbers like 4, 9, 16, 25, 36, 49, 64. These are the numbers I'm trying to figure out. So I can do it a couple different ways. I could go 10 and 20 and then break the 10 and the 20 down further. Or I could just say 100 multiplied by 2. Then I write it as square root of 100 times the square root of 2. And I know the square root of 100 is 10 times the square root of 2. Savannah wrote 25 and 8, which is also right. So Savannah, let's say you picked 25 and 8, because this is a really important point. And it's right. There's nothing wrong with that. 25 times 8. I'd write that as 2. And then I would take the square root of 25 as 5 times the square root of 8. And I'd end up here, and I got a different answer, and you're thinking, if I'm simplifying, shouldn't I end up at the same spot? I should end up at the same spot. It's the same thing. It's kind of like the fractions that we wrote at the very beginning. So what is the one step which I've forgotten when I've written this as the 25 and the 8? Because I'm not completely done yet. There's kind of one sort of problem I run into with this the 25 and the 8, which is the 5 and the root 8. Can anyone pick up on that? I don't see anybody typing anything, so maybe I'll just have to ruin the surprise for you guys. The 8. What's special about an 8? Well, I can break my 8 down further. So what is the largest perfect square that goes into 8, factors into 8? So I'm just going to keep the 5. The 8 I can write as 4 times 2. And then I can break that down into root 4 times root 2. Just carrying my 5 down, 5 times 2, root 2. And then I go 5 times 2, I know what that is, that's 10 times the square root of 2. And now I'm at the same spot. And this is something that happens all the time with these questions. You'll pull out a perfect square and you'll think, that's the biggest perfect square that's in there. And then you'll get an answer like the 5 root 8, so you'll end up here. And then you need to ask yourself, does the answer I've just gotten have any other perfect squares in it? And then you can recognize that a 4 and a 2 will give you that 8. So when we're simplifying, even though you think you've done it, you've done a step, there's a chance that you might actually have to do another step when you get to the end. So you just always want to make sure, once you get to what you think is the end, you look at the radical and say, is there anything under there that I could factor? And Savannah, I'm not trying to like ruin how you did the question. I'm just saying it's really important that we recognize that you can continue on. And you'd have no way of knowing that because this is the first time you've probably ever seen this stuff. So I'm glad you asked though, because that's, or mentioned it, because that's a really important point. The next one's a cube root. Now, I don't have my cube roots memorized as high as I should. And some of the cube root numbers get pretty big, so actually doing these questions requires a little bit of math, and you can always just write down the cube roots on your page as well. But 108, let's just think of my cube roots for a second. I'll just write them over here. If I go 2 cubed, I get 8. 3 cubed is 27. 4 cubed is 64. And 5 cubed is 125. So those are my perfect cubes. I need to figure out if any of those go into 108. So can I get 108 out of one of those? So I get 64. That's going to, 64 times 2 is 128, not 108. So that's not going to work. How about 27? 27 goes into 108 3 times? Did I get that right? 4 times. 4 times. So remember, we're dealing with cubes this time. Perfect cubes, not perfect squares. And that's going to be important here in a second. I'm going to write this as the cube root of 27 times 4. So 108, 27 is 4. Alex and Taylor are both on it. Now I'm going to break it down into 2 cube roots. we're going to have the cube root of 27 times the cube root of 4. And here's another spot where students will make some common mistakes. I bet you could probably guess what the common mistake is that students make. So I know the cube root of 27 because when I think about what number multiplied by itself 3 times gives me 27, I know that's 3. The common mistake students will make is with the cube root of 4. And because you haven't had a lot of exposure to cube roots, you see a radical sign, you see a 4, and you're like, oh, the cube root of 4 is just 2. But it's not, because these are cube roots. These are numbers multiplied by themselves 3 times that gives us whatever's under the radical sign. So there is no number, no integer number that will be multiplied by itself 3 times to give me 4. So I can't simplify this any further. I am satisfied with this 3 times the cube root of 4. I don't want to take the square root of the 4 because that's different than the cube root of the 4. So you need to just be careful with that. Last one here. We're trying to figure out the cube root of 128. I know it's not a perfect cube, so I'm going to have to try to simplify it. So of the perfect cubes that I wrote up above here, which one goes into 128 a whole number of times, or an integer amount of times? So we don't want to deal with decimals. We always just want whole numbers or integers. What number multiplied by maybe 2 or 3 or 4 gives me 128 of the ones I've written up there? So if I think 8, does 8 go into 128? So I go 128 divided by 8, and I get 16. So that works. I could do 8. Is there a bigger one? What about 27? Does 27 go into 128? Nope. It goes 4.7. Alex, you've picked 8 and 16, and 8 and 16 are both dealing with the perfect square. So 16 would be good for a perfect square, but not this. So I'm thinking of perfect cubes. How many times does 64 go into 128? So does it go in 128 divided by 64? That does go in 2 times. So what I'm going to do is I'm going to write this as the cube root of 64 times 2. And then I'm going to write it as 2 separate radicals, cubes, roots. Cube root of 64 times the cube root of 2. And the cube root of 64 is going to be 4. So I get 4 times the cube root of 2. That's my answer. If you had done the question and you went 128 and you divided it by 8, you would have got 16. So as an alternative method, you could have done it like this. You could have said 8's a perfect cube times 16. You've taken the cube root of 8, cube root of 16, and you would have said, oh, the cube root of 8 is 2, and then you would have ended up with the cube root of 16. And then you would have said, oh no, I got to what I thought was the end, but there's a perfect cube that goes into 16. What perfect cube goes into 16? So I'm just going to rewrite this. All right, I have this 2. I have the cube root of, I know 8 times 2 is 16. Cube root of 8. The cube root of 2. So I'm going to get 2 Cube root of 8 is 2 times cube root of 2, which now I've almost completely run out of room, is 2 times 2 is 4 times the cube root of 2, which is the same thing I had before. So if you go through these questions and you pull out a perfect square, you pull out a perfect cube, and you don't get to the, you didn't pull out the largest perfect square or perfect cube, it's fine. You get to your answer and you just need to recognize that this guy here, there is a perfect cube that goes into that still. So you kind of just need to do it again until you simplify it further. And then maybe you do it again and again until you get to a point where there's no other perfect squares or cubes that'll go into it. And at that point you're done. So I guess the important thing here is to just try to find the largest perfect cube or perfect square. If you don't find it, that's fine. You just do another step until you do find it. So notes, to make this process easier and reduce the number of steps, look for the largest perfect square inside of each radical. So if you can find the biggest one, you do it in one step. If you find smaller ones, that's fine. There's nothing wrong with doing it that way. You're just going to have a few more steps. And there's nothing wrong with doing it that way. So don't be afraid to do it that way. This is where we're really going to stretch your brains for today. Most students kind of get the simplification thing, but working backwards to get the 7 under the radical sign can get a bit tricky. So let's go with this. I'm just going to do the first one, and then some of you will just click and understand it right away, and then others will need to see it a few more times. What I want to do is, basically I'm working backwards. So I have a mixed radical, kind of like what I ended with in the last question, and I want to write it as an entire radical. So think of this as like 1.5. There's my mixed fraction. I want to go back to an entire fraction. I multiply the 1 by the 2 and then add it to the top. So I go 1 times 2 is 2, plus the 1 is 3 over 2. These are the same thing. 1.5 or 3 over 2, those are the same thing. So I'm going to do the same thing with radicals now. So I'm thinking, I need to get that 7 under a radical sign. So how did I get the 7 from a radical sign if I'm kind of like working backwards? So I can think of this way. I know that the square root of 49 gives me 7. Now I'm just going to drop the square root of 3 down. Now I also know that I can write these things under one radical sign. And then I can do the multiplication and get square root of 147. Whoa, crazy. So this is the exact opposite process of what we just did on the previous question. On the previous question, we would have started here and worked to the answer, the 7 over 3. In this question, not the 7 over 3, 7 root 3. In this question, we're actually starting at the 7 root 3, and then we're going that way to get it as an entire one. Let's look at an example. This one's cube root, so we need to think, how do I get 2 under a cube root sign? Or what number do I have to take the cube root of to end up with 2? Anybody think of that one? Probably have a good idea. I need to take the cube root of something to end up with 2, and then I have the cube root of 4. So right now I'm just dealing with this 2 here. What do I take the cube root of to end up with 2? What number multiplied by itself 3 times gives me 2? In this case, I'm going to go 2 times 2 times 2 is 8. And Alex was on it. And then I can say, I have two cubed roots. I can combine these under one radical sign or one cube root sign. So I'm going to write one big cube root sign, 8 times 4. And then just do the multiplication. 8 times 4 gives me 32. So I can take the cube root of 32. All right, 2 more. This next one's going to test if we're kind of really on the ball, because it's the 5th root, and I am not really that familiar with 5th roots. It's not something that happens a lot. Excellent question, Avery. Is there any way to combine a square root and a cube root? No. They're different things. It'd be like if you had x's and y's. If it said simplify and you had like 7x plus 2y plus 3x plus 2y, you can't combine your x's and y's together. They're different things. So same thing with the cube roots and square roots. They're different things. We're not going to combine them together. I say that, but we will actually eventually combine them together, but not right now. So no combining them together. Taylor's confused about getting the 49 and the 8. Okay? So let's do this question, Taylor, or everyone, if you want to think of it this way. Maybe I'll go to a simpler one. So the 7 root 3. So if I said, I give you the square root of 147, and I said, write it as a mixed radical. You don't even need to write this down if you don't want to. So you think, okay, red is a mixed radical. I'm going to figure out the largest. I'm going to figure out the largest perfect square, because I don't have a cubed or a fourth or a fifth or anything up front. I'm going to figure out the largest perfect square that goes into 147. You think to yourself, okay, 36 doesn't go in, and you check on your calculator and you keep doing divisions until you find one that fits in a whole number of times. And you say 49 goes in there. So I'm going to write this as 49 times 3. And then you're like, okay, square root of 49 is 7, and the square root of 3, I can't do that. So I get 7 root 3. So what I've just done is I've taken the exact same question here, and I've just worked backwards. Same thing. Just going the other way. I start at the 147, and now I'm going to the 7 root 3. So the 49 came from the fact that it's a perfect square. And if I can use these perfect squares, I can figure out these sorts of things. So let's maybe look at the last couple examples here, and might sort of help us out. As I said here, the 5th roots of things, I don't know. I don't have them memorized. So I'm actually going to have to do some work on my little calculator here. I need to get this 2 under a 5th root, because these both need to be 5th roots. So I'm thinking, what number multiplied by itself, or basically what's 2 times itself 5 times? We're going to maybe try out a new feature we've developed here. I don't know if this is going to work as well as we'd hope. All right. So here's my calculator, just a regular plain Jane scientific calculator. And I'm beside it and my hands in it at the same time. It's just like I'm in 2 places at once. Crazy. So what I'm going to do is I need to figure out the 5th root of 2, essentially. So I'm going to go 2 times 2 times 2 times 2. That's 4 times 2. So 2 multiplied by itself 5 times. What does that give us? Now, Alex, you've already put it into chat. I'm going to hit equals, and I end up with 32. So I know that the 5th root of 32 is 2. So I'm going to see if I can go back. I'm not going to be able to do this easily. back to my worksheet here. All right, so I know that the fifth root of 32 gives me 2. So Taylor and Alex both on it, which is really good. And then I can write this as an entire one. So I'm going to put the 5 out front. I have my 32 times my 3. 32 times 3 is going to be 96. And I get the fifth root of 96. All right, I want you guys to try D. The examples that are kind of included with these, the cube roots and the fifth roots and stuff are kind of maybe more extreme examples. You kind of will get a lot simpler ones to sort of start when you start doing the practice. So don't be stressed out about it. Be like, oh my God, I don't know these numbers and this is just so much work. And anyways, it'll come with practice, getting used to these things. And Taylor asks, so you multiply by the little 5. I guess if you want to think about it that way, that would work actually. You can multiply the thing in front by whatever's in front of the radical sign. The only thing you're going to run into is, I don't know if it's a problem, but with something like the square root of 5, we don't actually write a little 2 in front, but there is a 2 in front. And it's not multiplying by the 2, it's multiplying the number by itself as many times as the little number in front. So in this case, it's a 2, so it's not 2 times 4 gives me 8, because we didn't go 2 times 5 gives me 10, we went 2 multiplied by itself 5 times. So just like this one, we're going to do the 7 multiplied by itself 2 times. Last one, square root 80. I believe it is. Let's check. So I need to figure out how to get that 4 under a radical sign. And I know 4 times 4 is going to give me 16. So I'm going to write it as square root of 16 multiplied by square root of 5. Because I know the square root of 16 would give me 4, and I just end up with 4 root 5. I'm going to take it a step further. I'm going to say I can put both of these things under one radical sign, and then I'm just going to do the multiplication. And I end up with 80. And again, if you want to think about working backwards, if I had the root of 80, I'd say, what's the biggest perfect square that can fit under there? Again, you don't have to write this down. Say, oh, I know 16 goes in there. How many times? 5 times. 16 times 5 gives me 80. Square root of 16 times the square root of 5. Square root of 16 gives me 4 root 5. So this is working forwards, this is working backwards. Same thing. And that's kind of it. And I promise you that it's just going to be a little bit of practice. And if it doesn't make sense right now, once you get in and do a few questions, hopefully it'll start to make a little more sense. It's important that you start just kind of slowly and work your way into it. So maybe look at the learning guide here. We've done all this stuff, or should be, fairly well through most of this. Simplifying radicals is where we're at. So now we should be doing the simplifying radical section. So this is page 5. Write out the following as products of 2 radicals in as many ways as possible. So the first one here, the root 18. What can I write these as? I could write it as square root of 9 and 2. What other way can I get 18? I could get the square root of 6 and 3. And then I think, I need to circle the one that's a perfect square. So in this case, square root of 9 is a perfect square. So that's kind of how these questions are going to work. It's just helping you recognize the perfect squares that go into these. 24. I could have 12 and 2. I could have 8 and 3. And I could have 4 and 6. Where is my perfect square? I could have picked any one of these. I could have broken my 24 into either of these, this one, or this one, but only one of them has a perfect square in it. And this 4 and the 6 is the perfect square because of the 4. So that's the one I'm going to use. Number 4, simplify each of the following. This is kind of like what we just did, breaking these down. And we start really simple. So largest perfect square that goes into 8. Think to myself, 8, I could write that as a 4 and a 2, which is going to give me 2 root 2. So if you went onto your calculator right now and you plugged in the square root of 8, you get a decimal approximation, and then you plugged in 2 times the square root of 2, you should just get the same thing. They're both the same thing, they're just written in different ways. Kind of like the fraction. 1 over 2 is the same as 4 over 8. I can write that fraction more than one way, but I always end up with the same answer. Number 5 is writing it as entire radical. So you're going to try to get the 2 under a radical sign and then get them together as one radical. And then these ones are the same thing with the cube roots. And then same deal as cube roots. Same sort of idea here with A's and B's. I'm just going to write a star next to 8. When you are going through the work, when you get to 8, if you can simplify the numbers out front, awesome. Don't worry about the A's and B's for now. We haven't really spent time dealing with that, so maybe I'll go through that next day. And then a couple of questions. Cube has a volume, what's the length of each side? Should be able to do those, I think. Like terms, we'll deal with this next day. So not a ton of work, just a few questions, just some practice. Simplifying radicals, only the one section for today. Mrs. Ward isn't going to be on till 10:25, so you guys actually have 15 minutes. I'm just going to end it there. You guys could probably get most of this stuff done in the next 15, or you could grab a drink and a snack and wait for Mrs. Ward to come on. Does anybody have any questions before I leave for today? So I can put those in. Nobody's typing. Taylor might have a question. Yeah, the quizzes in the course you should be doing. I think the first one you can actually do comes after this section. So yeah, lesson 3 we've done today, and then the quiz number 1. So you should be able to do the quiz 1 after today's stuff. So if you're comfortable with what you've done today, you can have a go at quiz number 1. I'm pretty sure I turned off the timer on it, and I think there's 2 attempts on it. So just keep that in mind. I recommend you do it twice. It's the worst that could happen. And then there'll be a quiz after our lesson on Monday. And then that's it for this unit. It's a short one. The next day's material is, again, pretty straightforward. There's not a lot of terribly difficult stuff here. So we'll finish it up on Monday. And we'll write the test maybe by the end of next week. I don't want to leave it too long. I think I put a date in here, Friday, October 23rd. So you should be done by Friday. And Friday is a Pro D day, I believe, next week. So you could, if you got your review or your learning guide, what you're kind of working through this time in, then there you go. Awesome question. And should we do the quiz twice, even if we do well on the first attempt? I'll tell you this much. The test that you do is based out of the same questions as the quizzes. So if you did each quiz twice, they're just randomly chosen questions. You might get the same question on a quiz and then the next quiz, or you might get the same question on a quiz and then the test. So when you're doing the quizzes, it's always going to take your highest grade. Doesn't matter if you get 1 and 5, it just takes the 5. So I would personally probably do them each twice if I was allowed 2 attempts, because it exposes me to the same questions I might end up seeing again on the next attempt, or I might see the same question on a test or a question really similar. So I'm not going to say you have to, but if it were up to me, I probably would do them all twice, just for good practice. Even if you just went through it, you got 5, and then you just browse through it again to see what the questions look like, and you don't even need to submit your second attempt if you don't want to. It doesn't matter to me. There's no wrong there. I've given you 2 attempts. If you want to use them, then use them. So I'm going to leave it like that. That hopefully is a good spot to end. We'll wrap up this unit on Monday. We'll finish that test by hopefully next Friday. If you're still working through the Unit 2 stuff, send me a message if you need some help. I would really love it if we could finish that soon, very soon, because I don't want to leave it for too long. So thanks very much for signing in today, guys, and Mrs. Ward will be with you at 10:25. Thanks. Bye.